Welcome to the next video in this series. The topic of this video is atomic structure. In the last video, you learned about some of the fundamental particles, especially the electron, the proton, the neutron. And now we're going to see how these all are assembled together to form the basic materials that we have in the world around us. Here we go. So this brings us to our modern understanding of atomic and nuclear structure, which is electrons orbiting around a nucleus, which is made up here of a proton and also balanced by a neutron. And the size of the atom here is about 10 to the minus 10 meters, the tenth of a nanometer, and that has a special symbol in angstrom. The size of the nucleus, in contrast, is much smaller. It's about 2 to 10 femtometers. That's 10 to the minus 15 meters. So you'll see that the atom is mostly made up of empty space. And it's interesting to consider how we know that. And that's mostly due to the work of Ernest Rutherford, one of the most brilliant physicists ever, actually. And he set up a very elegant experiment to decipher the nature of atomic structure. So he did that by setting up an alpha source. I'll draw that here. It emits alpha particles, charged positive particles. Alpha particle is the same as the nucleus of a helium atom. And he scattered them through a thin gold foil here. And around the foil in the experiment, he placed a scintillating counter so that when a charged particle hit the scintillating counter, it made a flash of light. And he had collimated the whole experiment, so he had a thin beam of alpha particles coming through here in a sort of a line. So they would scatter off the gold foil, and you'd see them. He had his graduate students counting the scintillation events. Geiger was one of his graduate students. That's what they saw. A relatively small angle scattering, as you might expect, the interaction with the positive part of the nucleus. But once in a while, they saw an event that scattered backwards from the foil. And these were really interesting events, because if the atom is made up of sort of a soup of charged positive particles, they wouldn't scatter backwards like that. You have to have a head-on collision with something small and compact in order for the positive particle to scatter backwards. So let's consider the forces at work here, because it illustrates an important physical principle. I'm going to draw here the nucleus of the atom. It's positively charged, of course. And now we are sending in these positive charged particles, the alpha particles, towards the nucleus. Charge of 2 goes in, and it's kicked. As it comes in, it's kicked back out this way, like this. Okay, so there's a force acting between these two particles. What is it? It's called the Coulomb force. It's the force between any two charged particles. And you can write it like this. Force equals some constant k, it's just a number, times the charge of the particle. E here is a charge, and E for charge of the other particle divided by the distance between the two particles squared. So as you get closer, the force is more repulsive. This E you can write as E squared, that shows charge squared over distance squared. The closer they get, the more repulsed they are from each other. But now we have a problem here for the structure of the atom, because if you have a positive nucleus and here you have a negative electron, so these are going to be attracted to each other according to the Coulomb law. So as the electron orbits, it goes around, but it gets attracted more, so it goes into this kind of a spiral in towards the nucleus, and it's just not a stable structure. So that was a problem in the early 20th century, and that's where the new theory of the atom came in due to Niels Bohr. So the Bohr model of the atom is the quantum mechanical model, and here you'll see that the characteristic of this is that the electrons can only be found in discrete states, energy levels. Here the quantum levels of n equals 1, 2, 3, and 4. This is for the hydrogen atom, and you'll see the energy states here. The electron can transition between energy states. When it does, it emits a photon that's characteristic of the particular atom. So now let's review some of these concepts. We have the fact that light is a wave. It travels at a speed c related to the wavelength and the frequency. Also for those waves, they can be thought of as having an energy that's useful for, especially for X-rays, that's related to the frequency. In addition, for a massive particle, the energy and the mass are related to this equation. Here are some of the fundamental particles that you need to know about: the electron, the proton, the neutron, and the photon, having different charges and different masses. The photon has no mass. We have a force when a charged particle is next to another charged particle, the Coulomb force given by this equation, E squared over R squared. And also when a charged particle is moving in a magnetic field, it experiences this force proportional to charge times speed times magnetic field strength. And then finally, matter can be thought of as waves with this de Broglie wavelength given by either energy or momentum. Okay, I hope you found that useful. You understand a little bit now about how the atom is structured. In the next video, we'll start to talk about how the atom can decay and emit radioactive particles. I'm going to leave you with a little bit of further reading. And I would like to encourage you to go and do some problems. So the textbook that goes along with this video series has quite a few problems, about 10 per chapter. And I think the best way to learn physics is to do problems. So please go and do problems if you can. And we'll see you in the next video.